Astronomers have estimated that our universe could contain up to 1 septillion stars. In the Milky Way galaxy alone, there are more than 100 billion stars, including our very own Sun. Today, we can observe many different stars of various ages that all together paint a picture of what the full cycle of these celestial bodies are. Every star goes through dramatic change over its life cycle, spanning billions if not trillions of years. In this video, we will be going over the life and death of stars. Astronomers believe that stars form in large clouds of gas and dust called molecular clouds. Molecular clouds range from 1,000 to 10 million times the mass of the Sun and can span hundreds of light years in size. Dense regions in these clouds will begin to collapse, typically caused by collisions with another interstellar cloud, or the shock wave produced by a burst of energy from the formation of a new star or the explosion of a dying one. When this collapse occurs, the friction causes the contents of these dense regions to heat up, leading to the forming of protostars. At first, most of the protostar's energy will come from the heat released during the initial collapse, but after millions of years, the immense pressure and temperature of the star's core will begin the process of nuclear fusion, burning hydrogen atoms into helium. The release of energy caused by the star's heat prevents the star from further collapsing under the force of gravity. Once this occurs, a protostar becomes a main sequence star. Main sequence stars compose roughly 90% of the universe's stellar population. They range in luminosity, color, and size based on the mass of the star. The more massive a main sequence star, the brighter and bluer it is. Conversely, the less massive a main sequence star, the redder and less luminous it is. The mass of main sequence stars changes over time, and accordingly, the star's luminosity, size, and temperature will slowly change over millions or billions of years. Our Sun is midway through its main sequence stage. Since stars have a limited supply of hydrogen in their cores, they have a limited lifetime as a main sequence star. Astronomers can predict the lifetime of main sequence stars based on the ratio of mass to the luminosity, or in other words, the ratio of fuel supply to the rate of use. Despite a more massive star having more hydrogen within its core, it will burn at a higher rate to generate the energy that keeps it from collapsing under its own weight. Lower mass stars burn longer, dimmer, and cooler than their very massive counterparts. Some low mass stars will shine for trillions of years, longer than the universe has currently existed, while some massive stars will live for only a few million years. Once a low-mass star exhausts its core hydrogen supply, there is no longer any source of heat to support the core against gravity. Hydrogen burning continues in a shell around the core, causing the star to expand. It becomes redder, larger, and more luminous. It becomes a red giant star. When the Sun becomes a red giant, its atmosphere will envelop the Earth, and our planet will be consumed in a fiery death. Consider yourself lucky that this event will not occur until several billion years from now. Meanwhile, the core of the star collapses under gravity's pull until it reaches a high enough density to start burning helium into carbon. This phase will last roughly 100 million years before the helium supply is exhausted in the core. Some giants become unstable and pulsate, periodically inflating and ejecting some of their atmospheres. Ultimately, the core collapses and the outer layers of the star are expelled. The outer layers will form an expanding cloud of dust and gas referred to as a planetary nebula. All that's left of the star is its core, now referred to as a white dwarf. These celestial bodies are of similar size to the Earth, but with a mass comparable to that of the Sun, giving white dwarfs an unfathomable density. A white dwarf produces no heat of its own and will gradually cool over billions of years. In about 10 billion years after its time as a red giant, our Sun will become a white dwarf. Massive stars burn brighter and perish more dramatically than their low-mass counterparts. When a star that is 10 times more massive than the Sun exhausts the helium in its core, the nuclear fusion cycle continues. Fusion converts carbon into heavier elements up to iron. This cycle produces sufficient energy to keep the core from collapsing, but each new fuel depletes at a faster rate and lasts only a few million years. Once the core has reached fusing iron, the star will run out of fuel in a matter of days, as there is no energy to be gained by burning it to any heavier elements. Without any source of heat to balance the gravity, the iron core collapses until it reaches nuclear densities. This high-density core resists further collapse, causing the infalling matter to rebound off the core. This change creates a shock wave that travels outward through the star. The result is a huge explosion called a supernova, which injects carbon, oxygen, silicon, and other heavy elements up to iron into interstellar space. The fate of the neutron's core depends on the mass of the progenitor star. If the progenitor mass was around 10 times the mass of the Sun, the core will cool to form a neutron star. But if the progenitor mass was larger, then the resultant core is so heavy that not even nuclear forces can resist the pull of gravity. The core will collapse and form a black hole. However, the materials that were cast into the cosmos by the supernova and other stellar events will form further molecular clouds and become incorporated into future stars. Thus, the life cycle of stars begins anew.